Hello, everybody. Thanks for coming to our webinar again today. This is our 47th webinar since we started doing these in March. What we're going to talk about today is more about math channels, and it's a little bit of a different format than what we've done in the past. What we did is at the end of the last webinar, we asked all of the attendees to send us some information about math channels that maybe you've struggled with, or maybe some things that you'd like to see. And then we took that information. Emiliano has taken that information, and we've put together some maybe some more in-depth math channels, and maybe some different ways of looking at math channels. And I have learned a ton just from working with Emiliano as we get ready to go here. Some math channels I'd written in the past were maybe using extra things that I didn't need. And Emiliano will talk a little bit about that. And then we'll even step into some that are fairly complex, and all from users that sent some stuff in, questions about different math channels. So of course, we've only got about an hour here, so we can't get into probably every math channel that was sent in. So if you sent one and we did not talk about it, you and I, maybe we can chat offline, or maybe we'll do a second part of these, something depending on what we learn and what we see here today, and maybe some feedback from this one. But keep in mind that this is more about math channels, a bigger, deeper step than what we've maybe done in the past with math channels. So looking forward to chatting with all of you. Again, questions and answers into the question and answer box that Emiliano and I can see those, and then we may answer those as we kind of roll through. So keep that in mind. I want to start today with a quick poll that we haven't done polls too much lately, and kind of want to get a good handle on everything. What owned AIM devices do you have, and what do you use? There's a list there. I've only got 10 spots, and if yours is not in there, go ahead and just click on the other, and then type it into the chat box. We go back and review not only the questions and answers, but also things that came into the chat box as well. So there's a list there, all that apply. Go ahead and select it. That's a multiple choice, and start taking a look at that. I'm gonna let that play for maybe a minute or so, and then as we kind of move on to the introductions of Emiliano and chat about where we're gonna head, and then I'll come back and close that down. So the Emiliano is here. He's visited with us before. He's as a co-host on many different things, on simulation process with AIM, using AIM to do simulation stuff, and then also math channels and some other things in the past. We've done some things, and there we go. And Emiliano's been also in the background answering questions at almost every webinar. So appreciate him always being here. Just really believes in the webinars that we've been doing, and I appreciate that very much. I'm going to end the polling on that as Emiliano, as I ask him some questions about his introductions. Emiliano, a little bit of background on you. I know you've been around for quite some time. I first met you, gosh, we were going to the PRI show way down in maybe in the Orlando days, maybe even before that, back when it was first at Indy, before it went down to Orlando.
I think it was in Indy.
Yeah, so a long time, and one of the things I remember Emiliano, I think it was the first year we were there, at the end we broke down the booth and we were waiting, and we built paper airplanes, and the engineering in him was trying to see who could fly it the most and get it up to the roof. So that was my first meeting with Emiliano. Give us a little bit of background on you, Emiliano, and what brings you here, and what we're going to talk about a little bit today.
Yeah, I think you're recalling one of the crazy part of me. So thank you for this introduction. Anyway, thank you all for having me here. I've been around for 20 years now at AIM, and developing software of any kind, and I think very few words are needed for my career, and we can go ahead to the subject of today. That's math channels.
Yes, very good. And one of the other things I've said it here on some of these webinars before. One of the things I really like about Emiliano is he's not only the passion for motorsports, but then he and maybe because of that, he's not just a software guy that's sitting in the office writing software and understanding what we're doing, but he's out there at the track. You know, as the picture shows in the lower left-hand corner, I mean, he visits here in the States quite a bit, and plus, of course, he's at, you know, go-kart races and other forms of motorsports all over Europe as well. He really does enjoy motorsports as well. So there's a great tie here to have an enthusiast in there doing the you know, helping us with our software, and what you'll see is in some of the questions you guys may have, he because of that passion in motorsports, he's able to, you know, understand what you're trying to get to with your math channels and some other things. So looking forward to that as well. Okay, let's jump into, oops, jump right past. So the first thing we're going to talk about is, and we're going to just jump right in, right? What the plan today for how the video, how this presentation is going to go is we're going to have this presentation, which Robbie will link. If he hasn't done it already, Robbie is going to link this presentation because there's for you to download it if you wish to have it. It'll also be in the description box of the YouTube you know, recorded video here in just an hour or two after we get done. And the reason sometimes we don't need the presentation as much because it's just intros and outros, but in this case there's a lot of information in here, so you may want to click on the link that Robbie just put in the description, into the chat box, or grab it from the description later. So Emiliano, and so we're going to look at the presentation, then we're going to jump into Race Studio 2. We're going to build or look at math channels such as what we're building and show the resulting effect of that, and we're going to do a bunch of them, you know, as much time as we have, and then answer some questions and maybe build some different stuff. So Emiliano, we're going to start with this slide, talk about what you're trying to talk about here, and then we'll jump in. I'll be ready to jump into some data and take a look at it.
Yeah, the first thing I would like to speak of is an end condition. So how to build this condition when I'm in the need of a channel based upon the result of two other channels. Say I want to compute the coasting as a junction of two conditions. The first one being when I release the TPS, and the second one is that I still have to apply brake. That's what I call coasting. So I need the way I did it here is to compute a channel on the first condition. So saying basing on what we showed here in other previous webinars, I created the first condition that I call here A. It's a condition. It's a channel made of a math formula that is lower than TPS and 10. So this channel will give me a result of a 1 when it's true, and 0 when it's false. So when TPS will be lower than 10, it will be 1, and when it's higher than 10, it will give me 0. I then created another channel that I call condition B. It's lower than brake 10, so it means that it will give me a 1 when brake is lower than 10. Maybe there will be a difference between what we see here in the presentation and what will be in the DRK files, because when I build them, I use the bars for brake pressures, and in the DRK it's PSI. So we modified the math channel. That's the reason for which you will be seeing a difference. When I need a end condition, one of the way to create it is to multiply the two channels. So if you do A times B, you will be getting a 1, so you will be getting a true value when both of them will be 1. So when A is true and B is true, the result will be true as well. We can switch to the analysis, and so we can see this condition working.
That
Okay.
the process, as Emiliano's getting ready,
Mhm.
that the process of writing the math channel in that way, which let's look at it here in the data itself. We didn't change some of that yet, so maybe we will. But the process of writing it this way instead of I've done math channels like this and have shared math channels like this, but that point of using the multiplication symbol in the middle is for the and is it was something new to me, and it absolutely simplifies writing these channels. So I hope
Yeah.
everybody understands the distinction of what he's doing here, and it should make your ability to write these channels much quicker and much easier. So
yeah, the normal way should be using an if channel, but this way simplifies it a lot. I think you can keep your formulas very short using this process. And you can see here in the formula edit box, I simply had the first condition times the second one, and my channel is ready with a very simple formula. And it's pretty straightforward for what I know.
And you did include one that you'd already built before. I just want to make sure everybody sees this, but there's a break channel. All of these are just prefixes with EB, which is Emiliano Bina, his initials, and then BRK. So that's why you've got the EBs. Don't worry about that. So this is the break channel, and where he actually greater than, and we'll talk about this in just a moment. But since we included that, but front brake had to be 75 psi or 75 here. So don't worry about the one that is here. We're looking at when this gets activated, right? So okay. So that is the AND function, and an example of how to do that. And then what we can also then do is, you want to jump out and take a look at the result of this channel in the data?
Yes, absolutely.
Okay.
Yes.
So let's just jump out of this, and let's make sure coast is, let's turn on our coast channel. Okay. Let's leave throttle, let's leave speed, let's turn off some of these other ones, and we'll leave speed and coast. It also had the brake, brake pressure, and there it is up here. We'll just turn on those just so we can kind of see both of them. So now you've got your throttle here, and you've got your brake pressures, and then here's your coast channel and that's just the time between. Some of you have come up with the question, I'm sorry, Emiliano, but some of you have asked, how do I determine how long it takes to go from throttle to brake, right? And while he's calling it a coast, it really is the transition time from off of throttle before you start your brake, which is a great driver coaching tool that you might want to use, not just coasting.
It's a condition. It's a condition that has to be there for a minimum time, because you normally teach a racer to be very quick from full throttle to full brake in order to gain the maximum of what he can from the vehicle. And so you normally will be looking for these conditions into data and show your racer where it happens, and maybe you can speak with him on how to improve on this.
Okay. So, and by the way, this is the data that we're showing this in, is the data that we used a few sessions ago from Kenton Cook, and that the data, Robbie will, if he hasn't already, will post links to this data. And the reason we're resharing the data is the math channels are built, these math channels, so you don't have to re-import them if you don't want to. The math channels are already in this data file, and we took some of the other ones out. So if you want to take a look at this later, all these math channels are in here. Robbie has already linked these math channels as a standalone version if you want to import them into your own data as well, just so you understand it. And then if we zoom in real quickly on this particular one, and it's Kenton driving himself, and you can see where he's lifting off the throttle and getting after the brake, and it did not happen here. His feet are very, very quick, right? The only time we start to see it is when he's rolled off the brakes, he's letting the car roll a little bit before he starts to roll on the throttle, and we can see that there's that time that he was not on either pedal, and it's almost, and as I glance through here real quickly, it's always on the trailing side of these. He's very, very quick on his feet getting, you know, from the throttle to the brake, and all of the coasting, quote coasting, or, you know, off on, not on either pedal, is on the backside. So kind of
but
interesting.
when you move from the brake to the throttle again, we learned by Kenton that it has to happen.
Yeah.
And because it's one of the moment in which you have you maximize the lateral acceleration, so it has to happen. While moving from throttle to brake, it doesn't have to happen, and it doesn't happen in Kenton in Kenton data.
Yeah, very, very good. Okay, just there's one.
So
there's a quick explanation of what we're seeing, so that's pretty good.
Mm-hmm. Yeah, we can go back to the presentation, so we can
see the next one. Let me jump to the OR. There we go.
So we can also answer a question from Thijs. He asked if the plus is used for the OR. Yes, yes, it is. So when you need an OR condition is when you need to create to get a value out of two other channels, but you need to get a condition of true when one or the other one are true. So if you compute the first condition as I created here on Kenton data, I have a front brake and rear brake. So if I want a channel stating if I am braking, I can create a condition above either front or rear brake. So the first condition will be greater than front brake and the value of say 10 or whatever. So the threshold you want to set in your channel. You can create a second condition channel using always the greater than on the rear brake, and you set the threshold you like, and you can create a braking channel using front or rear using the plus. You can, in case you have for brake pressure sensor, you can create with using the plus an easy condition on 4 channels, or maybe you can use on either wheel. The result being different from 0, so being true, in case either one goes above the threshold you set. So if we can go back to data, sure, we can see I used this trick in my first channel, and it's one of the channel I used for demonstrating the end channel. Here I created a greater than 75 for either one of the two brake pressure sensors, and I use the plus to state that this channel is different from 0. So it's it can be either 1 or 2, but it's the condition making this channel appearing as true is that is different from 0. So in case all of them are true, this channel will be having a 2 value. It's not a 1, but mathematically it's different from 0, so the condition is true.
Okay. And you can, I think you mentioned on the slide, it's not limited to just two data points, and maybe one that some people might want to use this on is wheel speeds, and they want to get where there's a big difference in their wheel speeds for lockup or something like that, right? You can just start to stack up, you know, the 4 wheel speeds as well.
Yeah. Okay. You can, for example, create a condition on the wheel speeds, saying that so when the wheel speed is lower than say 10 miles an hour, it can be detected as a locked wheel, and you can create a math channel saying when you have at least one wheel locked. So you can easily create a NOR using the plus operator.
Perfect. The Brian put a question into the chat box, which I know you're probably not following. And Brian, that question we're going to get to here in just a little bit. So just so you know, in the chat, Brian, we're going to get to you in just a second with that specific question.
Yeah.
Okay. And so let's cancel out of there. Let's bring up that EC break just to take a look at it. And and as you mentioned, it jumps from 0 to 2 in this particular case, right? And when it was true.
Yeah, because all of the brake sensors are being applied, are being engaged on this condition. Yeah.
Okay. I hope you guys are seeing the distinct difference here. But some of those I've done some of these same things, but my math channels have ended up being much more complex, and this is a much easier, faster way to write these. So hopefully everybody is seeing that. You just have to worry about the 1, 2, or the 3, depending on how many channels you put into it. It's not just always going to go to a 1. It's going to go to something other than 0, and then you write your next one if you're going to use it based on something greater than 0 instead of equals 1, right? So
yeah, absolutely.
Okay. Okay, you got enough there, Emiliano? You want to run back to the presentation?
Yeah, yes, please.
Okay, let's go back there. We're gonna jump back and forth a lot today, fellas. Don't keep up. That's okay. But it
hold on.
Exactly. I think it's best because we can then describe it and then go show it, right? So it's this is the best way. Okay, derivatives. What's some tricks on derivatives?
Yes, there are very few tricks on derivative, but let's say that a derivative is a channel that normally has to be used when you could want to compute the variation of the channel. So you can for example use it in case you don't have any accelerometer on your vehicle and you have a velocity a speed channel. You can apply a derivative of speed and wow. I can read there's a mistake of mine in the presentation. Distance as a derivative of speed. No, it's acceleration as a derivative.
I'm sorry.
Of speed.
Yes.
I beg your pardon for this.
It is correct in the screen capture of the math channel dialog box, though.
No, the mistake is right there.
Yeah.
It's no distance equal derivative of speed. It's acceleration. So in case you don't have any accelerometer and you have only the speed, you can compute the derivative of speed, or maybe you can be applying this in case you want in case you need to do some very basic traction control basing on the variation of RPM. So maybe if you state that your RPM cannot raise above a certain level, you can compute it using the derivative of RPM. Or you can be computing the steering speed. Very often you have a steering position sensor and you want that gives you an angle and you want to compute the steering speed, because many people instruct racers in order to be as smooth as possible, in using the steering in order to avoid some phenomenon that apply to vehicle when you turn the steering wheel too fast
or too slow.
Too quickly, yes.
And we've had a number of driver coaches that have come on here and been part of our webinars that this is one of those things that they watch for, and they see how quick the driver's hands are, and if they're over, turning in too hard, too fast, and upsetting the car, they use the derivative of steering. It's just a speed of the change of a particular channel, and it's valuable not only in the 3 you've done here, but in throttle application and any number of things, right? So derivative, a very, very powerful tool.
Yeah, normally what you do with the derivative is moving from let's take these as example, steering from you move from angle to angle per second. So it's an angular angular rate. Something you need to take care of using the derivative is that mathematically this is an operation that tend to introduce noise into your calculations. So you normally need to apply a little bit of filtering of the channel when you compute the derivative. So in most cases, in a lot of cases, you need to be filtering both the result channel and the original channel. So you need to filter them in order to keep to keep the noise as low as possible.
Okay, so that's the first time we've introduced that in and I think in all of our webinars so far. We're still on the longitudinal one as far as selected here, but what you're saying here is is maybe we use a little bit of this filtering function, which we haven't talked a ton about. And you even mentioned that maybe even going back to the original channel and of the in this case the speed, but it could be steering or it could be
because the derivative tends to amplify the noise in the original signal. So
almost by definition, right?
Yeah, by definition, yeah. So you normally using the filters in the computed channel is enough. If it's not, you had better go on the original channel and filter also that one.
Okay, everybody take care of that. I mean, he talks about it there on the slide. Take care for noise, and so if you get something that is wildly out of sorts, or you see some big spikes where maybe there is some noise in the original channel, maybe you do some filtering to make sure this channel works correct for you.
Mm-hmm. Yeah. So we can jump to the live data, and we can see that I think I computed the longitudinal acceleration. Yeah, okay, longitudinal acceleration here. We can compare if we quickly have this with the longitudinal acceleration computed by GPS, just to show that those squiggly lines are really close.
The shape is very close. The numbers are a little bit different because
maybe I forgot to apply the correct conversion, because I think I should have to look at the formula. I think I just computed it as derivative.
Just the derivative. You didn't turn it into G's. It was just seconds of change, miles per hour change per second.
We can adjust it. Maybe.
How would we do it? How would we add that?
Well, we can compute the acceleration in feet per second square. So we need to be converting the speed into feet per second. We have a constant to do this. So okay. It's a GPS speed. Right inside the bracket is GPS speed times there's a constant that's.
And then feet per second.
It's a mile per hour, 2 feet per second. It's I think the third one. Okay, that one. Okay.
Okay, and then just a good habit to get into for everybody.
This one, as the original speed has been converted into feet per second, the result will be feet per second squared,
which is G's, right? I always like to just press the test.
G's. Feet per second squared is not G's. I think to convert it to G's, we have to divide by 32 something.
Oh, okay, so there's that value there. It did make it a little bit smaller, a little bit different, but do you know what else we would want to do with that in order to change that?
Divide by 32. Should be 32 1741 or.
There's the engineer in him that remembers things to the fourth digit, right? So
thank you.
And then rescale that, and now
we are close.
Now we're very, very close. Okay, yeah, so hey, we did it live. We showed the typical process of creating a math channel, right? You do it, you look at it, and you go, no, it's close, but it's and then we walked through the process. But it's wrong. But the shape was right, and then we walked our way through. So interesting and fun stuff. Okay.
Yeah. I see we have some questions. Maybe we take a little bit of time right after the next channel, or you want to take the time now?
Let's take a quick. Let's get through a couple of them real quickly. Could there be a way to say the position of some other channel during this coast position? What he's talking about is he's talking about the coast channel.
Mhm.
and the math of it, and he's wondering if is there a way to maybe add something to it, a third value where we can filter it down to even more of areas that we're interested in.
Yeah, you can. You can play with other end conditions, or maybe
Yeah. So we could
you,
just add an
you
and
can you
here,
can
and
combine.
only when it's in negative, when the longitudinal G's are in the negative, and then
Yeah,
you could only get it on the braking side, right? When you're coming off the throttle and onto the brake, things like that. We can, you could just add it as another and condition from what Emiliano
yeah,
was.
absolutely. You can add other conditions.
Perfect.
My suggestion is always to create a channel for one channel for every condition, in order to be checking, showing the single channel to be checking if the condition does what you look for, and then to use to combine the conditions into another channel. This way
Good
you will
point.
be using this way you will be using more channels, but you will be immediately viewing where you make a mistake, and how to fix it.
It will take your frustration level down because you can build the pieces, and
Yeah.
then build one more math channel and start to stitch them all together, and then where it breaks.
Mhm.
You know that your
Well,
individual pieces, and then when you get it done and you get it all put into one nice and clean and
yeah,
elegant math channel, then go ahead and delete the pieces ones out of your math channel list, and you're off and running. But it is very, very handy to build pieces so you know which piece is working, which one's right. Just like
yeah,
the longitudinal G, we wouldn't have known for a while there that it wasn't in G's, but it was in other units until we actually seen it and caught it. If we
yeah,
were doing that inside of a 4 or 5 part math channel, that would have been very difficult to find. So
yeah, absolutely.
perfect. The next, I mean the difference from upright to lean angle to calculate correct slip. So what he's looking at is a motorcycle and understanding when it's
Okay.
leaned out versus when it's up for the slip. But the
Okay.
same answer I think applies.
Yeah, absolutely, yes.
Tice talks about
Uh,
how much would you need to filter, or is it just trial and error? I'll let Emiliano answer in a minute, but for me,
most of
it's
the
always been
purpose.
trial and error for the way
Yeah,
I do it.
for me as well. For me as well.
Okay.
It depends. It strongly depends on how noisy is the original channel. Sometimes you can apply some tricks from a hardware point of view to filter noise away, or you can apply some tricks into the firmware to avoid noise. We have some powerful feature in our firmware to filter noise, and so normally the original with the current generation products is original channels are rather good, but it can still happen for maybe.
Yeah.
There can be conditions in which you cannot avoid the noise, and in these cases you decided to apply a filter here. And for the rest of the question, yes, it's for me it's kind of a try and fix.
Yeah, exactly. There you go. Okay, you want to jump out to the
Yeah, thank you.
presentation? Okay,
Yeah,
let me
yes,
jump
please.
out to that, and oops, missed it. Let me try it again. Come on, double clicking too
Okay.
quickly.
So
Next one is
after the
integrals.
Yeah, integrals is when I want to take care of how the effect of a single channel builds inside the session, or builds with time. So you I wrote that basically we are taking away the slash s
Per
from a
second,
channel.
yeah.
So
Yep.
yeah, slash second. Yeah, this is what we are doing. So just as an example that you can use this to compute the total amount of fuel used out of a consumption channel. So you can move from a fuel rate to to a total amount of fuel used.
Yeah.
Or as we are showing into the presentation, you can use, maybe say you are taking care for over revs in your car. and you want to know for how much time the over-rev condition has been matched during an entire session, and we did it into the DRK where we are showing. So we are jumping back to live data now, and we no, I don't think it's the TPS one, but it's the over-rev. It's a little bit lower in the list. Okay. Okay, we just one above. We created two conditions, one above more. Sorry,
okay.
It's RPM high. We created the first condition on the fact that the RPM is over 7,300. And another the condition the way to create the condition is very close to what we already did in the other channels a few minutes that I spoke about a few minutes ago. It's greater or equal engine speed 7,300. We created another condition on the TPS, and okay, this channel. We created the condition to see if the TPS is higher than 50%, just to decide if the racer is making this over-rev that we are speaking about in just 1 second. If they are making the over-rev while changing the gears up or down, just because we want to take care of these two different conditions. So if we can move down by one channel and go, okay, this one should be integral instead of lap integral, but it doesn't change its meaning a lot. Okay, thank you. So we are now matching an end of the two conditions. The one is RPM high and TPS high. So it will be true when both these conditions are true. So when RPM is over 7,300 and while TPS is higher than 50%. What's inside the brackets is 1 or 0 for what we created, and when we go integrating these 1 or 0 condition inside my sessions, the result will be a time. So I will get the total amount of time my engine is in these conditions, is in over-rev with the full with the throttle above 50%.
In our example, above 50%.
Yeah, in our example is above. You can you can state above 90%, so it's full throttle. Yeah, if you want, for sure, no problem. We can go to the TPS low. We are detecting here the over-revs when the driver is switching gears downwards. So when he's braking, this can be a very dangerous condition for some engines, some kind of engines, because this is a condition in which the vehicle inertia is moving the engine over the limiter. What did we do here? We reversed the condition on the TPS to reverse the conditions, so to create a not mathematical operation. We need to use the if function. So the inside part is if TPS is TPS high, I place a 0, and if TPS is instead low, I will place a 1. Other than this condition will be true when the total channel will be true when RPM is high, so it's over 7,300, and the TPS is low. we created this condition because it happens a very limited amount of times in these sessions. So we created this single channel just to spot where it happens, and the channel right below is the integral of the previous channel. So it will be giving me the total amount of time in which the high RPM with the low TPS condition is true. So we can show into the data where it happens.
I'll turn on the throttle positions just so we can see that, and then we'll come down here and we will go to the over-rev low, total, high.
Okay, perfect.
I think those are the channels we probably want to see.
Maybe yes, but I think the RPM high and TPS high will be very easy to show and to understand.
There you go.
It happens, yeah. Here. It happens.
So little. So such a little bit of time. He's talking about the over-rev. Over-rev with the throttle position low.
When the throttle position is low, it happens very limited amount of time. You can spot them very easily having this channel, and and
the reason is, just so everybody, people who were here, a couple weeks ago when Kenton was here with this data. This is a car with an ECU and with all the technology in it. So it's doing its auto blips on the way down, and it's even keeping from downshifting too soon. So it is rare that there will be a higher than a certain RPM when he's off the throttle. It's blipping, it's auto blipping, and all of that. So we did want to show that there are a couple of instances, but they were so rare that we wanted to show the actual channel. So your data may vary. At least my data would vary a lot. I would get a lot more of these if I was driving.
Okay. Yeah. Another thing we need to say is that this car has a rev limiter up to 7,500, and we inserted 7,300 just to explain the match channel.
Just to show
it doesn't happen in
real life. In real life, Kenton did a fantastic job. We had to almost force in some of the information here to make it look like there was some over-revs. So
yeah. Okay. So okay, I think we're done with this channel, and we can move along to the next one.
One thing I'm going to reiterate just one more time before I jump back to the presentation. We talked about the integrated and then integral and lap integral, right? And I just wanted to restate it one more time, where you can see where on this on the over-rev high, it's resetting to 0 every time because we use the lap integral function. And then this one, you see that it actually started at 3 seconds and climbs and continues to climb, and that's because we took off the lap prefix of the integral. And then what it does, if I zoom out on this, use the snap.
I think we can show. Oh, okay. You can zoom out. Okay.
You can see it actually counts the entire session. That's the difference between lap integral and integral. One of them resets at the end of every lap, and the other one counts the entire time. For those of you that are looking for time of low oil pressure or time of whatever it happens to be, understand that distinction between those two, because you can get one for the entire session and one for each lap. So very handy. Okay. Let me zoom back in, turn off the snap so we're ready to go when we get back, and jump back into the presentation for you.
Okay, thank you.
And I'll jump into, there you go. That's what you were starting to say, is that it's the same, but results in as a lap trigger. It resets. So useful for computing percentage, because you mentioned on the previous slide, take care for drift, and by resetting every lap, it sets it to 0 at the start finish line every time, which takes care of some possible drift, which is handy.
Yeah, some possible drift when for example, you want to apply integral to channels that need calibration. So if the channel is a little bit off calibration, the math process of integration that can be explained as a constant sum of the channel values. If your channel is off by a little bit, you can constantly sum up that a little bit off, and the result is that the channel drifts from its correct position.
Okay, perfect. And as we're as we jump ahead, Robbie, I noticed your response in a chat about math channels in general versus the test, sessions, and maybe find there's a video that we did a little while back talks about math channels, and we went through some of that general tab versus the laps, and how to share back and forth and automatically add your channels into every test you open. Maybe Robbie can get the link for that, so we don't have to chat too deeply about that here right now. So, and then the lap integral, Emiliano, I think you've covered that slide as well, right?
Yep.
Okay.
And the lap integral is useful for computing, for example, no, it's the next slide, please. For what is in this slide, I want to know the percentage of lap time that I spent at full throttle. Okay. So we can create a condition on the full throttle, saying a channel that is greater than TPS 90. So it will be 1 or true when I'm at full throttle practically. If I computed the lap integral of this, and then I divide by time and multiply by 100, I will be getting at the end of the lap the percentage I spent at full throttle. We can show it with real data, because I think it's better than 100 words from me.
Yeah, exactly. Percentage of full throttle. And what was the name? Full
TPS. It's just
full
just
TPS.
Okay. Full TPS.
Let me get over here where you can see that. Okay, this is a question that came up earlier, and we're answering that question as well.
Yeah. Okay, the full TPS is a channel that states when I am applying more than 90% of throttle, and we can compare it with the speed trace and see that that is correct. Then we I'd move to the one right below in the list, in the channels list on the left. Sorry, okay, full TPS. Full TPS is the integral of the previous channel. This is the time I spend at the full TPS, as we have shown just a few minutes ago. If I create a channel on a condition that is 1 or 0, and I apply an integral to that condition, I get time as a result. And this time at full TPS is the total amount of time. If I go at the end of a lap, I think it's roughly 100 seconds. Yeah, on a 2 minutes lap, that is roughly 93 seconds out of if I recall, it's a 2 minute and 4 second lap. So it's okay. Yep. Okay, it's right there. So if we move to the last to the bottom channel in the plot, this is the percentage time, the percentage I spent at full throttle. So if we can see at the very beginning of the lap, it's always 100, because it's the percentage that is gaining with time in my lap. So at the beginning, I'm always at full throttle. So at the time of the cursor, we have all the time spent at full throttle. So it will be 100%. And at the very end of the lap, I will be getting the value of the percentage at that time, computed on the lap. That is 75% roughly. The numbers on my screen are very
76,
very little, but
just a tick over 76. So you're real close.
Okay. So that's the result I have at the end of my lap.
we had the question earlier about this specific topic, and there's not a flaw, but just something you need to understand. If you're trying to report this out, it's a little bit difficult, because if, say, you brought it into a channels report and you just did the maximum value as a channel report, what you're going to get is 100, because that was the maximum amount of this channel. So this is one of those outputs that you almost have to come into the lap, put it near the end, and then you see the average time, or pick a specific spot, maybe exiting the carousel. You want to know how much ahead of that you are at full throttle, so you put the cursor there, and now all of a sudden you know that it was basically 78% of the time leading up to that, because it's real-time percentage wherever you put the cursor. So just keep that in mind as you're trying to understand what you're looking at there. That's why it's 100% at first, because the driver's at full throttle, and it's doing the math against the distance and the time, right? Percentage versus the time. Of course, it's 100% until he lifts, and then it's going to drop down and start to calculate it in real time.
And I see a question from Joe Atkinson in the Q&A box. Can we do the same with the amount of time spent going in a straight line? Yes. If you create a condition instead of full TPS, if you create a condition on a straight line that we are going to do in just a few minutes, you can say the amount of time you spent in a straight line. Yeah, for sure.
Yeah, you could do something
the amount of time or the percentage of
percentage,
of time that you spend.
Following those same exact paths. You could just come in on your statement, and instead of throttle position greater than 90, it could be lateral G less than the absolute value of 0.2 or something, right?
The straight line detection that we are going to explain in
maybe right about there in a minute, right? So we'll get into the deep. We didn't go the exact end result that you were after, but we did create that straight. Okay.
Yeah, awesome.
Okay.
So if we can go back to the presentation, we can.
And the next one.
Okay. The next one.
One more thing, and I know we're running out of time, but you mentioned down here, take care of channel frequency, and that's I've seen it on a couple of slides. I just wanted to touch on it here. When you're doing your math channel, what Emiliano was saying is you have the ability to do your sample rate here of the math channel, and it probably, what Emiliano might want you to do is match whatever the raw data coming into the math channel, probably match those sampling rates, I would think, right?
No, normally, yes. This is a thing you have to take care of.
Yeah, so I just wanted to make sure everybody's seen that little note there, and try to do that as best you can.
Yeah.
Okay, the next one.
The next one is the percent of lap time spent spent between 100 miles per hour or 120 miles per hour. You can create two conditions above speed. One is the one I'm above or equal. Okay, this is a 50 to 70 because we trained we tried a little bit of different combinations of channels, and we ended up with some mistakes in the presentation. It's my fault. Sorry. It should be greater or equal of 100 or lower than 120.
As the math channel shows, we just have to tweak these numbers over here, but the math channel is correct.
Okay, and then the trick is always the same. 100 times lap integral condition A times condition B divided by time as a function, and you will be getting at the running percentage as exactly the same as the channel that we showed one minute ago. So we can move to next slide. Okay.
Am I on the straight?
Am I on the straight line? There are several ways in which you can do this. You can create a condition on the lateral acceleration. You can create a condition on corner radius, and you can combine also those conditions together with the end function that we showed at the very beginning of the presentation. The condition I choose here is to compute the corner radius. using the square value of the speed divided by the lateral acceleration, and then to create a condition on this radius channel. If you are above 5,000 meters or 15,000 feet, you can safely state you are on a straight line. And using this condition, you can create also other channels, as Joe was asking a few minutes ago. If we can move on the live data, maybe we can show this this channel, how it works. Okay, thank you. So it's I think the two channels we need is are radius and the straight. So radius, it's kind of a crazy line. Yeah, it's because when you are on a straight line, this channel, its cornering radius, it's going to infinite, to an infinite value. And it tends to jump from a positive infinite to negative infinite. So it's a very crazy line. We can there are several ways to take care of it, but I think we can safely leave it there, and with the condition on the last channel that we can that on the last channel that is shown on the plot, that we can also show into a math channels. Here you can safely see that the condition is 1 is true when roughly when the green splits are shown in the top of the plot.
Yeah. Okay.
So there. Okay.
Yep.
Where the green, that the detection of the straight line that the map computing function in the analysis tool is taking when the radius is very high.
Yep.
You will be having a straight line.
Yeah.
So we can, if we can show just for a second the math channel window, we can show.
There's how we calculated the radius, and then there's the straight math
that's
channel that you talked about.
We are using a NOR operator using a plus, and our condition is when the radius is over 1,000, or it's 1,000 and sorry, over 1,000 or below minus 1,000. That's the condition for us to have a straight line.
And because of the way that this radius channel works, I'm just going to zoom in here so we can kind of see it a little bit more. Yeah. When you start to turn the corner, it's going to come from this near infinity, and it may be positive, maybe negative. And when it drops below the 1,000 mark is I think is what you use. So right there is where it has triggered and said, nope, now you're in a corner, right? You're no longer on the straight. When it was anything other than the inside that 1,000 foot left, positive or negative, you are on a straightaway. So okay, I just want everybody to see how it kind of worked. Okay,
that's the condition we have been asked for.
And some people might say, well, why don't you just use the steering wheel position, or something like that? Certainly you could. Not every car has a steering position, so this is a way to get to know when you're on the straight, either with radius, lateral G's, or steering position, if that's how you filter it down. So
and you can combine more of them.
Yeah. Okay. Perfect. Where would you like to go to next? Back to
the presentation, please.
The presentation.
So I think it's almost finished.
Yeah, we're getting close. Am I on the straight? Distance traveled by shifting. This is one of the ones that one of the questions that came in, and we chatted about it quite a bit. And Emiliano has come up with a way to do this.
It's yeah. No, I just I mean distance traveled. It's always a combination of and or conditions, and the integral or derivative. Most of the channels, most of the important channels are done with combination of those. I just wanted to point out that you can get this information using using the delta functions in the time distance plot. But I'm now acknowledging that most of our users already know this.
Yeah, and by the acknowledgement, we could probably write up a math channel and use tons of different conditions and try to get down to that what that one user was asking for. But in the end of at the end of this entire thing, it might just be better to go into your data and look at when to do the shift, use the delta, and you get the distance traveled right there. So we decided to skip on this one, saying yeah, we understand what you're asking, and we decided to just maybe punt and use the delta. So. This was an interesting one, and I'd like to finish on this one. We are at the time, but this one was one that I had done years ago, and frankly, I couldn't remember how I did it. And so I was very happy when I saw this question come in. And I know we're running late, and hopefully you guys can stay, because this is kind of the most powerful one we're going to talk about. And Emiliano, let's chat a little bit about what we're trying to do here is get the camber. Say you've got shock sensors, like we talked about last on Thursday. We've got shock sensors, so we know where our wheel is traveling in our suspension. And what the user was asking was, okay, I know what my cambers are at all of these different positions of my shock or of the wheel itself, right? And but what I really want to know is in my data, I want to be able to look at the data and say, what was my camber right at that point? Right, so we're looking to make this table, lack of a better word, you've done it mathematically here, but a table of getting from the spring and the travel in my suspension to what the camber actually is, because I've measured it and I know it. So I want to apply that and get an actual camber number. What have you done here? Kind of explain the process.
I took the data I was given, I placed into an Excel spreadsheet, and then I created a chart with its trend line. Then I took note of the trend line that's bold there, and I built a math channel using the equation of the trend line. So here the Y is the camber, and the X is the spring position. So just taking note of those numbers, I moved into the live data. We can go to the next slide, and I created a math channel.
And I have to switch data because we have another,
because it's on the other data that will be available also for people. Okay, here it is. Okay, right there.
I'd like to see this, and here was
right at the bottom. Okay, this is here in the formula box. I inserted exactly the same equation that is in the Excel spreadsheet. So is 0.0001 times the square of the suspension position that is computed as we showed in the latest webinar, I think, plus 0.017 times suspension position plus no, it's minus, sorry, 6 point something. And this is the equation that was given. This is the equation that was given me by the trend line in Excel. And the result is what we show here in the time distance plot. Okay.
So now here is the camber value, and here is the left front pot. But remembering from our discussion last weekend, last Thursday, the left front pot is just the sensor. We of course need to go through the motion ratios to get to the left front suspension position. So that's really the number we're kind of working off of, is this, and you've seen that in Emiliano's math channel. So now here is the movement of the suspension, and there is what the camber, the change in the camber based on that the numbers that we measured on the car.
Yes.
Okay.
Yeah, it is.
Very, very powerful. This is something that I had done on this particular car, this data, when we were racing MX5, and I also did it not only on the Camber, but on this particular car, there was it was a production-based race car, and there was some weird toe that would happen in the back, and then the driver was feeling that every time at a certain spot, and I couldn't figure it out. And then we cycled it, we figured out what the toe was doing when the car got, you know, to a certain set. And then after that, I created this same type of a thing, but I did it with toe out on the rear. And because of that, I could see when the car would get loose, and he would have to correct it because the toe was changing with the movement of the suspension. And I never could remember how to do it. And so I was so happy when I saw this question, and Emiliano was jumped on it and worked on it. So it was very good.
Thijs is asking, is that if Excel can create the formula from a trend line? Yes, it's into the settings of the trend line. The setting should be show equation in the graph. If you, it's a checkbox. If you flag it, you will be seeing the equation.
Perfect.
You've made my day.
On the Excel side.
Thanks.
In Excel. Okay.
Yeah.
And then follow the process that Emiliano mentioned in the presentation of where it fits into the formula, and then you are off and running. Mm-hmm. Okay. Perfect. Anything else that and Brian's mentioning, do you need to adjust for roll? My guess is there's another function there that we would probably want to work in there if you really wanted to really fine tune that. Yes.
Yeah. Normally, yes. Camber is adjusted with roll.
Would need to be adjusted towards that. And we have that data in we have roll. If you look down here, we've got front roll, we've got rear roll. We could, good point, Brian. We could stick that into the formula as well.
Yeah, absolutely.
Okay. Do you want to look at the data here? Or do you want to run back into the presentation?
No, I think we can safely run back into the presentation.
Okay.
And I think.
And there's the value, and we talked about you have to, of course, plug in the information. Yeah. We're not an Excel introduction channel here, right? So it's we're not going to go much deeper than that right there. If you want to, we can play with it. Right. Yeah. Oops. So, okay.
This is the way I created the formula. It's explained. Here. One thing you have to take care of is while you create the trend line in Excel is not to go too high with the polynomial order. So you stay with the second or third. Not go over that, because you are kind of overfitting your data, and the result will be I think wrong.
Too smoothed out. Yeah. Okay. Perfect. So that gives you some more information if you want to try this. A little bit more information on how to do this. So that's pretty good. The only difference, if you're looking at this slide, we did it earlier on the left front pot, but I think it's real important that you use the left front, use the motion ratios, and use the suspension, out at the tire, not at the sensor itself, if it's different. So, okay, perfect. Anything else you want to add about that one, Emiliano, before we jump to the next couple slides?
No, I think it can be enough.
we threw a lot at you this time, and I know it was awful quick, and maybe even skipped over a few little things, but watch the replay, give us a holler if we use some of your math channels and you're playing with them. Make sure you email Emiliano and I, and let's work the rest of the way through them and make sure they work in practice for you. If you are watching this later and you want to try some of this stuff out, you've got some contact information here in a moment. Try it on your own stuff. Maybe we end up chatting back and forth about how to make it work better for you. So, okay, let's jump. We've already jumped out a bunch of times. Kind of close this up now. Had a great time with this one. This one is one of those that are it's out of my comfort level. I'm not very good at the math channel, so I always learn just a ton, and so that makes this pretty fun for me as well. This video, along with all the rest of them that we do, will be up within about an hour or two of us finishing here, and this will make number 113 that we have up on our LearnFast e-training video site on YouTube. Check them out. There's tons of information there. Always check that description box. We put links to the sample data, the profiles, the math channels, And in this case, the presentation as well will all be in that description box. So if you didn't get it from Robbie, the link masters links in the chat box when we were doing it live, if you're watching this later, check down in the description box. You're going to have all the information so you can follow along. And maybe sometimes it's better to follow along a little bit with the math channels that are already built and then apply that information to your data as well. So sometimes it's an easier learning curve that way. So visit our YouTube site. There's tons of information there. The customer support, boy, we had virtually everybody was out at the track this weekend and had a great time. Great seeing all of our racers. I am going to travel for my very first trip. I've been scheduled to go to some, but they ended up getting canceled. They were in states and cities that didn't maybe allowed it to the last minute. But I will be traveling down to Laguna this coming weekend for a radical event. Looking forward to my first trip since March. So, going to be a good time. If not, of course, you can always call us, email us, and get a hold of us that way. So keep that in mind. The next webinar. Here we go. We've been doing we've chatted. I try to keep these more in line with what we're going to do next weekend as well. And Emiliano very real with his examples. We're going to have one next weekend. We're going to call it matching driver analysis to the driver, matching data analysis to the driver. David Free from D-Free Trackside Service is going to join us. He's been on our webinars, watching them for a long time. Him and I have been chatting back and forth with some questions and some, just dialogue back and forth. He's going to come join us. He runs a team where they support cars, trackside service, and they pull data out of the cars, and he's got a lot of experience with setting up the data and then chatting with the drivers and the crew and understanding what to look at, when to look at it, things like that. So I'm anxious to have David in here. Very thankful that he's going to come in and join us and give us just another perspective of how to use data in the real world at the track in something he does every single weekend. As Matt mentions in the chat box there, David's fresh back from a trip to Sebring. He's going to spend a couple days at Sebring even right after we do this as well. So down there racing, I think, next weekend. So looking forward to have David with us. David, thank you for agreeing to do this. Looking forward to just seeing how other people apply this knowledge and this information. It's always a great tool. We always learn from everybody that comes on here. Oops, I went one too far. Contact information. Emiliano threw a bunch of information out there. His email address is right there, software@aimsportline.com. Mine is there as well. If you want to talk math channels, boy, throw both of those emails in there into the two, and then throw it back at us. If I understand it and can help you, I of course will jump in. Emiliano's a much smarter guy than I am, and he can take care of some of the tougher ones, and then I learn as well. So it's a win-win for me. So it works out really well. So keep that in mind. There's some contact information. Boy, if you have any questions about what we talked about today, make sure you ask us. Emiliano, anything you got to in kind of closing for the end of our day here today?
Yeah, as usual, I had to thank you, all of you, and I learn as well, speaking with you all. And
absolutely,
yeah,
and I appreciate it. I know this is perfect, and I know it's a ton of work for you to put these things together, and we just got a bunch of emails. We weren't able to cover everybody's. I apologize for not covering everybody's, but keep them coming, and maybe we do another one of these a month down the road or something where we dig in a little bit deeper yet and look at some interesting ways of doing math in the functions. And on our way out, as I say goodbye, Emiliano also shared with me that certainly some of these ideas, while we just applied them to Race Studio 2, they are building and looking into the Race Studio 3 math functionality stuff that's happening right now. So a lot of the stuff you're talking about is being certainly planned on the next generation as well. So we appreciate all of that information you've given us as well.
Okay.
Thank you, Emiliano. Thank you, everybody, for showing up. Make sure you come and visit us again on Thursday at the same time. So we will see you all later. Talk to you soon.
Bye-bye.